There is a $2 compound that makes any squeaking, slipping, or glazed engine belt run completely silent and grip perfectly forever. Not temporarily, not for a few weeks until the noise returns, permanently. One application on the belt surface and the friction coefficient that has been degrading since the day the belt was installed restores itself at the molecular level. Dealerships charge between $150 and $300 to diagnose and replace a squeaking serpentine belt that, in the vast majority of cases, has not failed structurally and does not need replacement. The belt replacement industry generates over $2 billion annually in North America from serpentine belts, alternator belts, power steering belts, and accessory drive belts that are replaced based on noise and slipping symptoms rather than actual structural failure. And a $2 beeswax and pine resin compound that harness makers in the 17th century used to condition drive belts on water mill machinery that automotive engineers documented in technical literature in 1938, and that the belt replacement industry has spent 80 years ensuring you never think to apply, has been sitting in hardware stores and beekeeping supply catalogs the entire time. Not because the application is technically demanding, because it is not. Because anyone with a $2 block of beeswax, a pinch of pine rosin, and 30 seconds with the engine running can achieve what a dealership charges $250 to replace. This is the story of natural belt dressing. The drive belt conditioning compound that powered the Industrial Revolution, that mill engineers and factory mechanics used for 2 centuries to maintain leather and early rubber belts in perfect working condition, and that the automotive parts replacement industry quietly ensured disappeared from public knowledge the moment synthetic rubber belts became the standard and replacement became more profitable than maintenance. Welcome to Forbidden Camping. If this knowledge matters to you, the subscribe button and the bell are how you make sure it survives. Let me take you back to where this story begins. Not in a dealership service bay and not in an auto parts store, but in a textile mill in Lancashire, England, sometime around 1790. A mill engineer named James Arkwright, nephew of the famous inventor Richard Arkwright, is managing a cotton spinning facility that depends entirely on leather drive belts to transfer power from a central water wheel to dozens of spinning frames spread across the mill floor. The leather belts run continuously for 12 to 16 hours a day, 6 days a week. They slip, they squeak, they dry out and crack, and every minute a belt is slipping or being replaced is a minute the spinning frames are not producing cloth. Arkwright develops a conditioning compound from materials available in any rural Lancashire household. Rendered beeswax from the estate's hives, combined with pine rosin collected from the pine forests on the property, melted together and allowed to solidify into a block. Applied to the running belt surface by holding the block against the inside face of the belt while the machinery is in motion, the compound melts from friction heat and distributes itself evenly across the belt contact surface. The result is immediate and dramatic. A slipping belt grips. A squeaking belt silences. A dried and cracking leather surface becomes supple, flexible, and mechanically conditioned, and the treatment lasts for weeks of continuous operation before reapplication is needed. Arkwright's compound circulates through the Lancashire textile industry within a decade. By 1810, variations of beeswax and pine rosin belt dressing are standard maintenance practice in every major textile mill in England. Engineering manuals of the period documented as essential knowledge for anyone responsible for maintaining power transmission machinery. The Mechanics magazine, one of the most widely read technical publications of the early 19th century, published a detailed article on belt dressing formulations and application techniques in its 1825 edition, describing the beeswax and rosin mixture as the universally recommended compound for leather belt conditioning in industrial applications. The chemistry behind why it works is straightforward. Leather and rubber belt surfaces lose their grip through 2 distinct mechanisms. The first is surface glazing, where repeated compression and heat from belt pulley contact causes the outermost layer of the belt surface to become smooth and hard, reducing the microscopic surface roughness that provides mechanical grip. The second is surface contamination, where oil mist, dust, and moisture accumulate on the belt surface and act as lubricants between the belt and pulley, reducing friction and causing slipping. Beeswax addresses both mechanisms simultaneously. The long-chain hydrocarbon molecules in beeswax penetrate the surface microstructure of rubber and leather belt materials and restore the elastic compliance of the surface layer, reversing the glazing effect and restoring the microscopic surface texture that provides mechanical grip. The wax molecules also displace the oil, water, and dust contamination from the belt surface by preferential adsorption, replacing the slippery contamination layer with a controlled friction surface. Pine rosin, which is a mixture of abiotic acid and related resin acids, adds a tackifying effect to the wax treatment. Resin acids have a natural adhesive affinity for rubber surfaces, increasing the coefficient of friction between the treated belt surface and the metal pulley above the baseline grip of the clean belt. This is the same reason violin players apply rosin to their bow hair, the same reason gymnasts apply chalk to their hands, and the same reason that every leather craftsman in pre-industrial Europe kept a block of pine rosin in their workshop. Resin increases grip. It has done so reliably for thousands of years. A paper published in the Transactions of the American Society of Mechanical Engineers in 1938 by an engineer named Howard Crane documented the comparative performance of beeswax and rosin belt dressing against commercial petroleum-based belt dressing, compounds on rubber automotive drive belts in controlled testing. Crane's measurements showed that the beeswax and rosin treatment produced a coefficient of friction recovery of between 85 and 95% of original belt performance on glazed and slipping test belts, comparable to the performance of commercial products costing between 5 and 15 times more per application. The study was published in a professional engineering journal and noted that the natural compound had the additional advantage of being non-damaging to rubber belt materials over extended use, unlike some petroleum-based dressings which caused accelerated rubber degradation. The study was published in 1938. It was cited in mechanical engineering literature for several decades. And then automotive rubber belt technology advanced. Synthetic rubber compounds became standard, and the replacement industry that had been building around automotive belt maintenance found something far more profitable than a $2 maintenance compound that kept belts working indefinitely. They found the replacement belt sale. Now here's where the story takes the turn they do not want you to follow. The modern serpentine belt is an engineering marvel. A single continuous belt that drives the alternator, power steering pump, air conditioning compressor, water pump, and multiple other accessories from a single crankshaft pulley. It is made from ethylene propylene diene monomer rubber, a synthetic material with excellent heat resistance, flexibility, and longevity under normal operating conditions. But EPDM rubber serpentine belts fail through surface degradation long before they fail structurally. The outer surface of the belt, the rib surface that contacts the pulley grooves, develops microcracking and glazing through repeated thermal cycling and compression. This surface degradation causes squealing noise and intermittent slipping under high accessory loads, particularly on cold mornings when the rubber is less flexible and on hot afternoons when the air conditioning compressor creates peak belt loading. The auto parts industry and dealership service model have trained both mechanics and consumers to interpret serpentine belt squeal and slip as evidence of structural belt failure requiring immediate replacement. The diagnostic procedure at most service shops involves inspecting the belt for visible cracks, measuring its length for stretch, and checking the tension or spring rate. If the belt squeals or slips and shows any of these symptoms, replacement is recommended regardless of whether the underlying cause. The beeswax and rosin compound does not evaporate. The wax molecules penetrate the rubber surface and remain there. The rosin acids bond to the rubber polymer chains and alter the surface friction characteristics in a way that does not wash off, evaporate, or migrate. A single application treats the surface degradation at the material level rather than masking it with a temporary film. The squeal does not return because the condition that caused the squeal, the glazed and contaminated belt surface, has been permanently corrected. In 2018, a shade tree mechanic in Texas named Billy Garrett began documenting beeswax and rosin belt treatments on a YouTube channel after his 2009 Ford F-150 developed a severe serpentine belt squeal that a Ford dealership quoted him $220 to repair through belt and tensioner replacement. He applied a beeswax and rosin block to the running belt surface, following a technique he had found in a 1950s automotive maintenance manual at an estate sale. The squeal eliminated immediately. He documented the results with before and after audio recordings and posted the video online. The video accumulated over 1.2 million views. The comment section filled with viewers reporting successful treatments on their own vehicles. Ford dealership forums responded with warnings about voided warranties and potential belt damage from improper compounds. None of those warnings addressed the 1938 ASME study confirming the safety and effectiveness of beeswax and rosin on rubber belts. The comment section did not care. The results were documented and reproducible and cost $2. Now here is exactly what to do. And like everything in this vault, it is almost insultingly simple. Purchase a block of pure beeswax from a beekeeping supply store, a craft supply store, or online. A 100-gram block costs between $1 and $3 and is sufficient for dozens of treatments. Purchase pine rosin, also sold as violin rosin or bow rosin at music supply stores, or as pine pitch at hardware and outdoor supply stores. A small block costs between $1 and $2. Melt the beeswax and pine rosin together in a ratio of approximately 3 parts beeswax to 1 part rosin by volume. Use a small metal container in a water bath, never direct heat, as both materials are flammable. Stir until fully combined and pour into a small block mold or an old tin container. Allow to solidify completely. Your belt dressing compound is ready. With the engine running and the belt moving, hold the compound block lightly against the flat back surface of the serpentine belt, not the ribbed contact surface, for approximately 5 to 10 seconds. The friction from the moving belt will melt a thin layer of the compound onto the belt surface. The compound will distribute itself across the full belt width and transfer onto the pulley contact surfaces through normal belt operation within a few minutes of running. You will hear the squeal reduce and typically eliminate within 30 seconds of application as the compound reaches the full belt circuit. Allow the engine to run for 5 minutes after application to fully distribute the treatment before switching off. For belts with severe glazing that has been developing for an extended period, a second application the following day after the first treatment has fully distributed achieves maximum restoration of the belt surface friction characteristics. Do not apply the compound to the ribbed inner surface of the belt that contacts the pulley grooves directly. Apply only to the flat back surface and allow the compound to transfer and migrate to the contact surfaces through normal operation. Direct application to the pulley contact surface can temporarily reduce grip during the first few minutes of operation before the compound has distributed to its equilibrium concentration. The treatment is safe for all rubber belt types, including EPDM serpentine belts, V-belts, timing belt external surfaces, and accessory drive belts. It does not accelerate rubber degradation, does not cause belt stretch, and does not affect the belt's tensioner operation. The 1938 ASME study and decades of practical application in industrial machinery confirm its material compatibility with rubber drive surfaces. Total cost of the treatment, $2 for materials that will last through dozens of applications on multiple vehicles. Compare that to a serpentine belt replacement at $150 to $250 in parts plus 1 to 2 hours of labor. Compare it to commercial belt dressing spray at $8 to $15 per can that requires reapplication every few weeks. Compare it to the tensioner replacement that often gets bundled with the belt replacement for an additional $75 to $150 because the tensioner shows no structural fault, but the service writer includes it while the belt is already off. A retired mechanic in rural Georgia named Earl Washington has maintained every belt on every vehicle and piece of farm equipment he has owned since 1978, using a beeswax and rosin block he makes himself from his own bees and pine trees on his property. His oldest documented belt is a hydraulic pump drive belt on a 1971 farm tractor that has been in continuous seasonal service for over 40 years with beeswax and rosin maintenance and has never been replaced. He described the maintenance practice in a letter to a farming publication in 2015, noting that he had watched neighbors spend thousands of dollars on belt replacements over the decades for equipment running alongside his own that he had never needed to address beyond the annual wax treatment. 40 years, one belt, $2 of maintenance per year. The serpentine belt on your car that has been making that cold morning squeal for the last 3 winters does not know it is supposed to cost $250 to fix. The alternator belt on your truck that slips under heavy electrical load in summer heat does not know that 30 seconds with a $2 wax block is all that stands between it and silent, reliable operation. But you do now. The dealership service writer who quoted you $250 for belt replacement built a revenue model on the assumption that squealing belts mean failing belts, and failing belts mean replacement sales. The commercial belt dressing industry built a repeat purchase cycle on the assumption that a product that works for 3 weeks is more commercially valuable than a product that works permanently. The automotive training curriculum built its diagnostic procedures around replacement options because replacement generates labor hours and parts margins, and the $2 maintenance alternative generates neither. None of those assumptions survive contact with a beeswax and rosin block, 30 seconds with a running engine, and the knowledge that Lancashire Mill engineers figured this out in 1790 and kept industrial machinery running for 200 years on the same $2 principle. Some knowledge does not disappear. It waits in an 1825 issue of the Mechanics magazine where mill engineers published it as essential knowledge for anyone maintaining power transmission machinery. It survives in a 1938 ASME technical paper that confirmed its effectiveness on automotive rubber belts and was quietly left out of every automotive service training program written afterward. It exists in the gap between $2 of beeswax and rosin and the $250 service appointment that uses your lack of this knowledge as its entire business model. That gap is $248 wide, and now it belongs to you. If this vault changed how you hear that cold morning belt squeal on your way to work tomorrow, subscribe and share this video. Every share puts a crack in the wall they spent decades building around knowledge that was never theirs to lock away. Every subscription keeps this channel digging deeper into the vaults they thought were sealed forever. The next vault opens soon, and what is inside is the one thing every driver pays to replace every 30,000 miles that an engineer in 1959 proved never wears out at all.